A very good morning, good afternoon, or good evening, depending on where you are. Welcome to this webinar about aquathermal energy and fifth generation district heat and cold. My name is Rowan Benning and I will be your chair today. Today's webinar is organized by two organizations, two Dutch organizations, the Dutch Netwerk Aquathermie and KNW, the Royal Dutch Waternetwerk. Netwerk Aquathermie started in 2019 through a Green Deal Aquathermie, and 20 parties signed an agreement and agreed that they would accelerate the energy transition by mapping value and application of aquathermal energy. Today there are over 65 parties involved in the network, and activities involve around knowledge development around aquathermal energy, knowledge sharing like today, and developing the network further. The Royal Dutch Water Network is an independent knowledge platform for the water sector. They focus on a broader focus with everything related to water. They organize every 2 years the Amsterdam International Water Week, and this event is at the same time as the water trade show for processed drinking and wastewater, Aquatech. Both events, the Amsterdam International Water Week and Aquatech, will take place this year in November. The events focus on sharing knowledge and expertise in the field of water and delta technology. For today, after I have given a little bit of an introduction, we will have a presentation by Herman Eidens. He will give an introduction into fifth generation district heat and cold and a little bit of the history about this concept. There will be time to answer some questions after his presentation, and then we'll give the word to Hugh Moore. He is from the Scottish company Clyde Gateway, and he will tell us about what they're currently doing in their project with aquathermal energy and fifth generation district heat and cold. A little bit over half time, we will go into some breakout rooms. You will have the opportunity to get to know the other people that are here today present and are interested in this topic, and there's time for a little discussion. Around 5, we'll recap the discussion and work towards the end of the webinar. A few announcements for today's webinar. Please ask all your questions via the chat. We might not be able to answer all of them, but we will provide a Q&A, a written Q&A after the webinar. This webinar is recorded until the breakout rooms. We'll have a small questionnaire at the end of the webinar because this is the first time we've been doing this webinar, this international webinar, and we would love to hear your thoughts about it and if you have any ideas for a follow-up. The recording, the Q&A and presentation will all be published and sent to you after the webinar. So Herman will give a little introduction into 5GDHC. I'll tell you a little bit about aquathermal energy, just to make sure we're all on the same page on that topic as well. So aquathermal energy, heating and cooling buildings sustainably by using heat and cold from water. We recognize 3 types. That is thermal energy from surface water or ocean and seawater, thermal energy from wastewater, and thermal energy from drinking water. Because aquathermal energy is a low temperature source, it's the most effective in well-isolated buildings. And when we use aquathermal energy for heating, there's always a heat pump involved to make sure we reach the right temperature. Expectations for the Netherlands is that by 2030 there will be over 200,000 buildings heated with aquathermy. And with that very short introduction about aquathermal energy, I would like to hand over the word to Herman Eidens. Herman, the floor is all yours.
Thank you so much, Rowan. So I will share my screen. My name is Herman Eidams indeed, and I'm talking to you from my former position when I was Director of Innovation and Strategy for the MijnWater company. And from this company, we initiated the D2Grids project. I will come back to that later. Because that's kind of basis that we did a lot of work on heat grids and cooling grids, and where I'm showing you some results now in this introduction. Actually,
we don't see your presentation yet, Herman.
I share again. Should be fine. Please tell me. Okay, so that was the first sheet. You didn't miss anything. Go to the second sheet. If we look into district heating and cooling grids, but actually it's more district heating grids, we have a long history. It's more than 100 years. We see it started somewhere in 1880. And this picture is from Aalborg University in Denmark and Sweden, where they have a lot of these grids and a lot of experience. And they made a kind of classification of grids from first to fourth generation. And actually what you see in this picture is that those grids are coming down in temperature and they are adding up in green resources. So if we look in the fourth generation, we see a big Christmas tree filled with all kind of sources like data center, like solar, like wind energy, feeding those district heating grids and making them more sustainable. But there is one thing that you also can see in the picture, that all those grids are central based. And if we do a big central plant, which is feeding a district heating grid, then we have some disadvantages. And one disadvantage could be if you have a city of like 10,000 dwellings, you will feed this grid always dependent on the weakest point in the city. So if one building is very bad insulated, you still will have to give a high temperature. If they change those buildings, like insulation or other modifications, it's very hard to give a tailor-made solution to them, because you are central based and you cannot adjust your system to individual changes of end users. Also, you have to deliver 24/7, so those grids have quite big energy losses, also because they are on a higher temperature level. Specifically, if they go for domestic hot water in summer, we know that they can have losses up to 70%, and they don't integrate cooling. And I go to my next sheet. Now, if we make some step back and look into grid developments, then on certain fields, we see that we can classify those grids in central-based, in decentralized, or distributed. And on the right side, the distributed grids, that's also what we call the cloud grids. And from other fields of science, like IT sector, we can see that we made a shift from a central-based systems where we all had the big mainframes to decentralized and to cloud structures. And that's actually something that we were looking for in this D2Grids project. If we can make this move with thermal grids also, that we go from a more central base to decentralized. You already see this in power grids. If you have a local solar PV panels on your roof, you are making the first step towards decentralized grids. Actually, if we look at our system, what we built in the city of Heerlen, which was one of the front runners in this, what we now call fifth generation district heating cooling concepts, then you see that you still have some sources on the left side. It could be a windmill or solar park, but what you use is electricity only. And that's quite a major issue now in the Netherlands. So we want to get from natural gas and we want to decarbonize our fuels for our power for this kind of systems. So then we feed this grid from a big seasonal heat storage, which is a coal mine actually in the city of Heerlen. And we get a warm pipe, which is running on 25 degrees from the source. And we have another cold well, which is giving us 18 degrees. And then if we go to the first building, they have a decentralized energy substation. That could be an industry, that could be asking for cooling. If they do, then we take water from the cold pipe, the 60 or the 18 degree, and we will, from the backside, from the heat pump, feed a higher temperature into the hot pipe. Actually, now I'm telling it the wrong way around for this picture, but if they need heat, they will take the heat from the warm pipe and they will inject colder water into the cold pipe. So after this substation, my warm pipe still is 25 degrees, but I cool down the cold pipe by 2 degrees back to 16. And so if I go through the city all the way and I have different consumers, some needing heat, some needing cold, and then my pipes are getting better all the way because I'm always reinforcing from the backside of the heat pump. And this has a kind of benefits, has a number of benefits. So due to the low temperature of those pipes, I can bring in gains, low temperature gains. So if I have a data center giving me 40 degrees Celsius, it's welcome because it's, again, improving the temperature level in my grid. If I have local green resources, I can share them, the energy between different end users using this thermal grid. We see that modern buildings do have a cooling need of 35% of the total energy for heating and cooling and 65%. So if we exchange those energy flows, then we only would need at the end 30% had to feed the total system. Of course, then if we want to exchange, we need also storage, and that would be a large storage as we had in the mines, but there could be other city-based storages. But also we want on the district level storages keeping, and in the buildings itself, keeping those energy for the time that passes between the supply of, or the availability and the demand of energy. And actually what we do also, that we have those heat pumps running on very powerful water, which makes that I do have a very good performance, what we call the CUP, and also have a very long lifetime.
2 minutes.
Okay, you are stressing me. So looking back at what we actually were doing there, and then we said we came up to 5 principles. We said what we want in this district energy system is to first close the loops. As I said, if I take heat, then I give cold back and I don't blow it from the roof into the air. But also I'm using low-graded sources for a low-graded demand. So I'm not burning flames 1000 degrees Celsius just to heat up a building by 20 degrees. And I'm running a system which is decentralized and demand driven, avoiding those losses, as I said, going up to 70%. Well, moreover, what we want to do is to integrate different energy sectors. So that could be waste energy from industry or from transport, which is very useful for my building sector, and we want to bring it as local as possible. And we don't say that we wouldn't need the Sahara or the North Sea to feed our energy system, but if it's in your backyard, first take your backyard and then go further away. And actually, if you have those principles, what we did there is that we, in this project, and we have 5 pilots from Glasgow, you will tell afterwards, also in Paris, in Bochum, in the Netherlands, and in Plymouth, that we were checking if we can derive KPIs for those 5 principles. So can we show a good performance of the system by setting up formulas, which will give us insight in how we perform on those principles, which actually are ideals. And if you do this, you can get a label out of it. That could be for one reason that you get like financing or quality assurance on your system, but much more we think it could help us to improve those systems if we want to make steps forward and if we are planning new additions or expansions of the system, what kind of add-up would improve this performance of your system. Actually, it's important where you put your monitoring and your system boundary. I won't go into detail now because I have limited time. And then if we look at we have a number of benefits from this kind of fifth generation district heating cooling grids. And the first is that those decentralized installations give us the opportunity to adapt to end user modifications, that we have those heat gains available, and we use the backside of the heat pump to keep this energy in the system, and also that we can provide cooling. If you look a bit further, then we see, and this is some results coming from scientific papers, what we found for the last 2 years, that we see that we have a great reduction in of these temperatures, leading to a great reduction in power consumption per square meter of building. It's about 40%. If we go from third to fourth generation, we see savings of in the order of 5% or 3%. But if we go to fifth generation, we find reductions in cost in the order of 40 to 50%, also for carbon emissions and also for primary energy use. So even if we compare to conventional gas-fired systems, then we find a great increase of performance. This is from 2 pilots reported 58 and 48% of less carbon emissions and 35 and 78% reduction in cost. And even if we bring into these systems also our own electricity generation, then we can even make it better and get very close to energy neutral districts. There is some barriers if we want to build those systems, and actually the most important thing, I think what we are facing, the most important challenge is how can we speed up the process, and that will be by integrating this kind of development into a broader urban infrastructure planning. What also very important, and that has to do with the time between building and connecting end consumers, that we get loans which have a very low interest. We need plug and play connections, and they must be foolproof. And we need to go towards prefabricated substations. Because if we have to do tailor-made work, it will be cost too much time, too much cost, and it will give us too much complaints that things are going wrong. We should avoid.
Thank you very much, Herman. We're running out of time.
One more line and then I'm finished, Rowan. Okay. And we have a lot of resilience. So here is some prizes we won. You can read that in my presentation. This is some project that we did in the European level. You also can find the links in the presentation. And this is my final sheet showing you the website of D2Grids, where you can find a lot of information about what we did in the project and also toolkits and guidelines and trainings and everything. Thank you so much, Rowan.
Thank you, Herman. Could you maybe put yourself on mute, because I'm not sure if the sound wasn't that great when I spoke before. So I see a first question coming in about, let me see, about slide 9. If you talk about the cost reduction, is this on the CAPEX or the OPEX side? And can you say something about what are typical total cost for the system and maintenance elements?
Yeah, of course. And kind of difficult question because you always have local circumstances which can be on a huge influence. What I can say more or less, but don't crucify me afterwards, there we had some kind of investment around 20,000 euros for one dwelling in the city of Heerlen. And then we were quite close to a business case, lacking some like 5,000 euros per dwelling. But that was on the old gas prices 2 years ago. So now we see that gas prices went up 2 times. So I think if we do a proper job and go for some low-hanging fruit, then we can find a business case and make some money on these systems.
All right, thank you very much, Herman. Unfortunately, we don't have time to go further into the details of the questions that have been asked through the chat. I would like to hand over the word to Hugh Moore from Clyde Gateway. Hugh, the floor is yours.
Good afternoon, everyone. I'm Hugh Moore from Clyde Gateway, which is the largest regeneration company in Scotland. And I'm just going to show you a wee bit about what we've been doing in Scotland in relation to 5G DHC. Hopefully you can see my slides, can you?
Yes.
Okay, so I'll take you through these. So we're delighted to have been involved with MijnWater and other European partners that Herman's mentioned in delivering our D2 Grids pilot. This is Glasgow, for those of you who aren't familiar with us. This is our city of Glasgow, and Clyde Gateway sits in the red area that you can see on the map, where we're adjacent to the River Clyde, which is a river that runs through Glasgow, and the adjacent local authority, which is South Lanarkshire Council. The main sort of drivers for us in terms of net zero has been the government's objective to achieve net zero by 2045. And most recently, although we've done a historic energy and master plan, the Climate Change Acts of 2019 and the designation of our area as a Green Regeneration Innovation District have driven our opportunity to look at local energy generation and resilience. And most recently, in terms of policy publications, heat networks and heat and building acts have been published. And we have our own, through our local authorities, local heat and energy efficiency strategies which need to be completed by the end of this year. And those are looking at zoning areas effectively for district heating and cooling opportunities. The Clyde mission that I've mentioned at the bottom there is really a reference to the River Clyde again, where those key water sources exist. So the river, wastewater are our key areas of investigation. So the opportunity for us has largely focused on, and I'm showing us a 3D model here in terms of not only the river and wastewater, where wastewater treatment works are obviously adjacent most of our river sources, but also shallow geothermal mine workings as an opportunity from the historic mines that have been mining that's been undertaken in the Glasgow region. This is translated into our key sort of energy project areas. Our green area there shows our traditional district heating scheme, very familiar to, I'm sure, our European friends on the call, largely looking at combined heat and power solutions, but clearly we're moving from that to renewable energy sources as quickly as possible. So it's been a fairly quick learning curve in the Scottish context from our community energy project here, but moving to wastewater energy solutions. This is not only looking at sewer facilities and where wastewater is being generated, but also most recently looking at hydropower applied to wastewater resources. We have significant levels of wastewater treatment works and sources available in the Scottish context, and part of that issue is to try and maximise the opportunity to access strategic resources that can generate heat, cooling and power indeed towards net zero objectives. And this is obviously the trend that you'll be familiar with in the European context, but in the Scottish context, moving much more quickly towards this as a solution and breaking from the sort of traditional routes in terms of power and heat production. Our installed capacity for our D2 Grids project is a relatively simple scheme. As you can see here, it's abstraction pumps that are directly applied to the treated effluent. These can obviously be expanded and upgraded and increased to reflect the capacity, substantial capacity that's available within the wastewater treatment works. And this is part of the facilities that are owned and managed by Scottish Water, our national water company. And this is also a key point reflected in the commercials that Herman's touched on, where we are seeing these elements as passive supplies at a relatively cheaper cost, around ½ per kilowatt hour being delivered, and that being reflected in the affordability of these types of schemes to local customers. In the Clyde Gateway context, we've used our Smart Bridge facility, which joins our two communities together, that also has ducts for 5th generation plastic pipe systems that can join communities and deal with the diversity of heating and cooling requirements between different types of buildings, again, which Herman's also referred to. We have taken the view that in terms of project deliverables, all generation elements are being directed from the energy centre. But in this instance, we've looked at, as Herman's touched on, modular buildings being delivered to site to improve the cost efficiency. So you can see that in the energy centre in item 4. This is a bespoke energy system that's being delivered to the site, but also we have focused on ground-based solar arrays to enhance the solar capacity and the potential for integrating thermal and solar grids within the community. In the schematic, this is reflected here in terms of the abstraction system, the heat exchangers, the incorporation of heat pumps in the energy substations and solar panels, solar array to support future development. And this very much reflects what Herman's been talking about, the decentralisation that 5G DXC can provide, the ability to minimise the waste and use the ambient loop that's shown in green here, effectively connecting each of the buildings, the ability to make best use of heating and cooling within the ambient loop, and coupled with the power grid can improve efficiency substantially. For the Glasgow project, we've applied principles that Herman's been talking around, particularly around the closed loop system. And we perform well in relation to that energy supplied from external sources and using low-grade heat, and similarly focusing on the demand-driven energy supplies and quantifying the decentralisation of the system. We're very much focused on that, and that's certainly improving the bottom line in terms of the revenue position, the OPEX position for the project. The integrated approach to energy flows is very much dependent on the customer expectations as well, but that reflects what we hope to connect to the system over the medium term. And also principle 5, focusing on local resources as a priority. We do well, obviously, in terms of the wastewater energy resources. These make a substantial impact on the bottom line. But in terms of the proximity of energy sources, these again need to be upgraded as modular development and growth of the system is developed. So in terms of our sort of spider diagram, this is how the Glasgow project looks. Perform well in many areas that we've referred to in terms of low-grade sources and the availability of wastewater. But where we need to expand in terms of 4.1 and 5.2 on this graph is essentially that growth in customer connections. So the more we can do that in a modular context, the more efficient and effectively profitable the scheme will be. What we're producing at the moment in our renewable project is that access to wastewater heat. We have collaboration agreements with Scottish Water Horizons, so that is the regulatory element between us. We own and manage that network, but we can scale that network to reflect the customer connections that we are dealing with in terms of developer frameworks and programs. It's a substantial capacity that's available through the sewage and heat recovery system, as you can see from the graph there, and the outputs that can be delivered. What we need to focus on are a range of constraints that exist around the electrical network, probably many that are familiar to you, but certainly that's an area that we think we can develop and grow from over the next medium term, and focusing on particularly things around the different approach that's needed for 5G DHC, the significance of the Internet of Things in terms of smart technology to improve the management and efficiencies of schemes, and as well as the challenges about growth and how we do that. As a regeneration company, we take very much an infrastructure first approach. The problem with that, obviously, is that customers are that bit further down the line, and that's an area we're improving on in terms of trying to impact not only on new development, but in also retrofit of existing buildings. And this is one of the buildings, Red Tree Magenta as we call it, that we're looking to retrofit as part of the existing deliverables, as well as any new buildings, and diversifying to residential as we develop. And that's a sort of future image of how we will see 5G DHC rolled out in our area over the next 5 to 7 years. So I hope I've covered that presentation reasonably quickly for you.
Thank you, Hugh. That was perfect, actually. Maybe you can stop. Yeah, there we go. Stop sharing your screen and just see your face. We actually got two questions in the chat, and both are about the energy price and how is there a fixed cost per unit of energy, or is there a variable hourly price depending on the amount of renewable energy available? So how is the accounting done for smaller or larger consumers? Is there a difference?
Yeah, we haven't applied that yet, simply because of the fairly limited range of customers at the moment. But our model is largely based on the figures that we'd identified as comparables in our counterfactual. So working that out around heat being supplied at around £40 per megawatt hour and cooling at £80 per megawatt hour. We've applied those in relation to the peer comparisons that we have from elsewhere. They're considered relatively discounted levels in relation to other providers. But as part of our objective as an urban regeneration agency and the social and economic aspects to income generation and addressing fuel poverty, etc., we've tended to target them at those levels as they are currently. There may be some subtleties around different types of users, but at this stage, those are still the guides that we are using at the moment.
All right. Another question that came in is, what are the temperatures you're running in the network, or what are the expected temperatures that will run?
So the treated effluent is being delivered on average between 9 and 12 degrees before it enters the river, and that's what's being supplied into the ambient loop. It can vary obviously a wee bit from that, and depending on seasonality, but essentially that's the variations that are going to appear within the ambient loop. So the colder pipe being maybe around 5 degrees, the warmer pipe around 11-12 degrees. Within that, then being supplied via the energy centre to the heat pumps, we are looking at delivery temperatures of around 60 to 65 degrees to the end users.
Okay. Another question is about working with Scottish Water. How open is the local water company to tap the energy from the wastewater? Are there any limitations to the use of wastewater infrastructure?
No, that's probably the good thing in many ways, that because it's a public company, we can engage very openly, open book approach to the heat supply agreements or the energy supply agreements we have with them. They obviously have their own drivers in terms of carbon reductions and use of renewable energy sources. So we are very much on the same equation, if you like, for what we need to do as companies, as part of our government objectives as well. So that works fairly openly, and the resource that's available from the wastewater is indeed substantial. And with a view to increasing that, the only limiting factor at the moment is largely around customer connections.
All right. A question which relates to that a little bit. Are there any legislation or boundary conditions in regards to the impact of extracting the energy from the water from when it goes back to the river?
Yeah, so the Scottish Environmental Protection Agency, or SEPA as is known, would have a role in terms of that. But what we've identified in terms of the locations where the wastewater is being treated and then deposited via the Clyde or via the river, the differential is somewhere between 1 to 2 degrees. So effectively it has very, very limited impact on the regulatory elements through SEPA.
All right. One last question, I think, so far on the chat. Do you already add CO2 pricing to your models, for example, to your CAPEX or OPEX?
We don't actually have that applied in the model as such. It's probably an element that's identified via the counterfactual. And that has changed certainly over the period. So in terms of the gas counterfactual, to the changes that have taken place in the energy statements that are required now for development, we are seeing a much less of a differential in respect of that comparison. But we quantify that separately from the more general elements.
All right. Thank you very much. I think that's the question so far. If there are any other questions coming up, I would say we can tackle those later with the Q&A that we will be providing to everyone. Thank you so much, Hugh. Then I would like to go to the next part of our program. We'll be sharing my screen shortly again. We will be going into breakout rooms shortly. I would say my colleague Carla can now stop the recording of this webinar and start setting up the breakout rooms. We have about 20 minutes for that, so I would say take perhaps